afternoon thing, and it's going to be part of the same theme as sort of the kickoff to the whole Simons thing. I've been a vagabond for, emphasis on the bond at the back, for part of this year, and had the pleasure of time at Stanford with my friends, and then at the Institute, and some of these ideas, at least the newer aspects, helped in the many conversations I had there. What you heard about was our effort of B squared FH. That's a joke, but I'm not going to explain it. It's a state of hubris. It's one of the most famous papers in all of astronomy, and I would not say that our paper, if it's ever done, will be as famous. But the thing that we heard about was Zeta fluctuations that arise from in a secondary manner, and that it can be described as associated with trajectories that involve an instability, heating, and the way you take the non-Gaussianity of the short scales and make it into something that we can observe is by long wavelength modulation. So there's no direct relationship of the non-Gaussian Ks that you're building here. It's all associated with the low K modulation. One way or another, what you saw is intimately related to particle creation. The question is exactly how. And I'll say a few words about that because it's one of the things that I think is really physically interesting. But what you get out of this, and this is the regime, this is an inflaton as a function of ln A, intermittent, secondary, uncorrelated fluctuations with the primary. The power in zeta is much more localized, and therefore what it means is relative to the very stringent constraints we get from the data, it is more controllable in a sense because it's fundamentally intermittent. So there are higher order endpoint functions, even coherent endpoint functions, and so you can, without any trouble at all, evade the Planck 2018 FNL constraints, which you haven't seen yet, but I have, and that'll be coming out this fall, but it's not dramatically different from what you already know. So this isn't what I'm going to be talking about. I'm going to be talking about a different regime where we took this kind of basic instability ballistic idea, and we decided within the context, more or less with a stochastic inflation framework in mind, we decided to work our way back into the inflationary regime. So fundamental to this, as has been discussed, and even within tunneling, is there are a lot of things that you can understand fully classically, and classical things have a lot to teach us even when H bar is important, and that's one of the things I'm going to emphasize. So it's B2FM, a B, and an F, but I want to highlight somebody who's just started as a graduate student with me, Tom Morrison, who is been working on this subject. So we are thinking about transverse directions, and you'll see instabilities in transverse directions, which makes it rather different than here for reasons that I'll explain. And the kind of fluctuations in zeta that you generate are what you might call primary ones in the sense that they're intimately related to the usual inflaton one, whereas here they are secondary ones. What that means, among other things, is that they're correlated with the zeta fluctuation. So you might say, I'm really worried about that because that's what Planck played the big constraints on. It is the correlated nonlinearities of zeta that allowed Planck to put such powerful errors. It isn't error bars. And it isn't just that. It's correlated and they're everywhere. So it's very different from the intermittent where they're here, there, but not everywhere, which means that the statistics have to be done differently. In order to, we think, understand this because of the nature of it, which I will explain as we go along, you have to go beyond the standard stochastic inflation kind of picture. That doesn't mean that you want to throw it out the door. It means that you want to think more about the stochastic term that's driving the long wavelength coarse-grained evolution and try and make it a little more realistic than the standard thing that we have been using all these years, which is, roughly speaking, a Hawking temperature doing the feed of the coarse-grained. So an aspect of this, and you will see that this goes in my mind from many, many years ago, is that you consider localized features on the potential surface in the transverse direction. And that builds structure associated with an effective wave number, an effective sort of pivot scale for phi, and that corresponds to an HA dynamically. And so what you would see, instead of having ubiquitous non-Gaussianity, there would be characteristic scales associated with it, which is also something that Planck didn't look for as well as it can be. What we have gotten out of this, so our idea is to just make a fundamental instability of the same sort of instability that you heard Andre talking about. So what this means is that you take a little quantum fluctuation in the transverse direction and you stretch it out by an instability. You can call it a tachyon mode because people in particle physics like to use that terminology, but it's just a general instability. It's associated with m squared negative, that there is a direction in which there's instability, and that was sort of much the basis of this. This turns out, at least what we've done so far, is that it's pretty hard to avoid getting a two-point function burst. It's a burst in k, and so you don't have, as I'll show in a minute, you don't have much capability in the observable range to do a lot of p zeta fooling around because the Planck results are so powerful in terms of determination of p zeta from the data. And so, of course, what you do is you hide this, and you know where you hide it? You hide it in primordial black holes. No, you actually push it off into the range that you can, that corresponds to the large-scale structure region where we have the really good constraints. But you also get here bursts of 3 points, 4 points, and it'll just keep going up. And it's intimately related, these ideas, to particle creation. And that is something that I think is a really rich thing to explore, in spite of the fact that it's effectively a classical phenomena involving the stretching out of what started as quantum fluctuations, and you're just stretching them out in some sort of classical way. Sorry about that. If you chain these things together, you can get repetitive bursts. And that's sort of what trapped inflation does. It's what Eva has done a lot of. And it is, in fact, related to trapped inflation, as we talked about on Sunday on the bus over. And what you'll find quite remarkable is we've already got the equations solved, and we have some results. Now what am I doing? You'll see it. Okay. This is not a Planck talk, but I have to show my favorite diagram from Planck because that's one of the ones that we produced, Shiji Wang and I and Andre over there. And it shows the most remarkable thing that comes out of Planck. Whoops. What did you do? Comes out of Planck, which is that this is a fit to the p zeta spectrum. It includes the BK14 data. I could tell you, which I'll have to be killed if I tell you this, but BK15 doesn't make very much difference to this figure. There are these bands in which we're determining zeta, and so what is amazing is that there are all of these bands, and it's uniform NS. Uniform NS isn't something that's because you chose one parameter and NS happens to fit. It is what the data wants. Then as you start to go into the regime where sample variance or cosmic variance is allowing more trajectories being allowed, there is this great interesting anomaly that we spent a lot of time thinking, is there anything significant about it? And then there are large fluctuations once you go beyond about 1 megaparsec inverse, and there is a huge amount of room for doing great damage to uniformity in zeta in that territory, and I'll show you how we can do a lot of damage down there. Just in passing for the anomaly here, it's pretty similar to the 2015 anomaly, but you see the deviation from this uniform law is just minus 0.26 plus or minus 0.13. 2 sigma. 2 sigma, nothing bigger than 2 sigma. And so you can't say I'm going to throw out the standard model of cosmology on the basis of that. For those of you who like it, you can refer to this in terms of entropy, and I'm an entropy fan. It's 3 bits of deviation from the standard model, which is not very much. And here's the NS that uses this data, forcing it. This, and you'll see how many significant digits. My good friends here love those significant digits. And that's actually an ensemble average value. That is that slope. So you do the uniform NS, you do this multi-band thing, and that's what you get. I can't resist in passing. You add all of this degrees of freedom, and you still get a remarkable R limit relative to the uniform NS case. That's history. Oh, no, it was just to draw the line. But let me also say, this was m squared phi squared, long ruled out. This is the 1 and 2 sigma thing that's allowed by BK14. And it doesn't change that much with BK15. And then this is the mean line. So that's showing the, I mean, this is like giving you the snapshot of all of the neat stuff from Planck in one figure. And of course, it's a famous Bond figure, which means that it's colorful and complex. And okay. So I'm going to quickly walk through a few words here. The general issue that we are exploring at Zeta is the role of classical evolution instabilities in particle creation, in heating during and also during inflation, and the role that that plays in non-Gaussianity generation. The tool, as you've heard, are these classical lattice grid calculations. The quantum fluctuations come in as classical random field sources. And we evolve a whole bunch of phi fields, the momenta, H, and alpha is often a very good time variable to use. Because it's a lattice calculation, what you'd like to do is to put in all of the nonlinear gravities and do a fully general relativistic calculation. We don't do that, but we think that we capture a lot of it by working on uniform ln A hypersurfaces, and H is constrained by its relationship to the fields. I'll skip that. Shiji Wang, who's part of our generalized group, has got a lattice code with full quadratic nonlinearities for gravity in. But that hasn't been explored as much as it might be for some of these issues. So Andre's story was oscillate plus instability leads to nonlinear mode-mode coupling, coarse-grained entropy generation of Shannon entropy in this shock in time. There is another kind of entropy, Kolmogorov-Sinai entropy, which is really interesting, which is the precursor to the Shannon entropy, and it is basically telling you what the instabilities are like in terms of a measure, and that'll become a bit clearer as I go along. How do you tie it to particle creation? The way this has usually been done in preheating is that you take the energy density that you calculate with the lattice calculations, you say, okay, I'm going to try and identify a good h bar omega, which is time dependent. I divide them, and that's going to be my occupation index. And what tends to happen is you see that the occupation index comes along, and then something happens, goes up, something happens, and that's what particle creation is. It's why we didn't like it in this story. We have a better way to do that, we think, in terms of entropy that allows for the possibility of bursts of particle production. And that's what we're trying to put into the framework for the during inflation non-Gaussianity as well. Okay, so as I said, quantum fluctuations are there, but as seeds for the instabilities, which are largely classical, not unlike thinking about bremsstrahlung and other production mechanisms that occur in just ordinary classical classical mechanics. Okay, then Jonathan also dealt with that. I was going to go through a little bit of history of how I'm sort of where I'm at on some of these things, because we did a lot of response functions, especially associated with instabilities, a long time ago, that the desire was to see how we could build mountains of power and valleys of power for zeta and also non-Gaussianity. And then in the early 90s with Salopek, we built on Vilenkin-Starobinsky stochastic inflation. If I do say so, this paper, which never appeared, did it a lot better. And it fully related the field and the momentum. And as you will see, there's a really nice expression and way to think about this in terms of quantum diffusion and a quantum diffusion velocity. But it's missing terms. We recognized this at the time, that you could do all sorts of interesting phenomena as you cross the horizon in terms of things sort of accelerating, and that the only way you could go after that is by some new kind of way of calculating things like this. The other aspect, which I think is true, and I'm very convinced it is now, is that we always talk about the long wavelength field as a condensate, but we never really think about it as a condensate, and yet it is a condensate in my view, and I'll try and say something about that as we go along. And then the other thing is that classical evolutions are really useful. So the question is, do you always want to throw that out in a quantum mechanical treatment? And I think the answer is no, and there's a way to try and get around that, which involves the use of coherent states, which contain all of the information that is needed quantum mechanically, but it is much more closely tied to classical concepts, which means that you can use lattice calculations to feed into that. And then we're into the instabilities. Okay, I'm going to skip over this. This is just showing old zeta stuff. And the only thing I want to emphasize here is the concept of a effective m squared acting on a field, which goes negative, and then it goes positive. But the main point is instability is fundamental, and you can get large modifications of zeta as a consequence of instabilities. A long time ago, we made these mountains of extra power. It was all done self-consistently, and now so strongly constrained, but we're going to move the territory to much higher k, where the constraints are much less. Okay, this is my one-page slide telling you how stochastic inflation works, and I think I'll skip over that and have it as the last slide. But it's probably looking at it differently than you do. But it's pretty neat because the Fokker-Planck equation has two terms in it, and a key thing is this diffusion velocity, which contains h bar and describes and is described in terms of the gradient of an entropy. So I'll leave that concept, and we'll come to it at the end. And I'm going to get to the model calculation that we're doing, which is trying to go beyond the stochastic picture via lattice calculation, where we're putting in initial fluctuations at short scales, but we're allowing the system to fully evolve, and we're seeing what the response is. And the basic picture, as you will, maybe I'll go to this one that'll make it clearer. Yeah. The basic picture is that we have a usual inflation, an out inflation, where nothing beyond the inflaton really happens, and then we create a localized instability. And so with trapped inflation, the way it worked is that this would be curled up, and then there would be a little bit of m squared equals 0. But what they weren't doing, unless you correct me, is that they weren't doing m squared negative in the transverse direction. The m squared negative in the transverse direction can lead to really remarkable phenomenon, and we saw that in the way back when with Salopek and Bardeen, and now we'll see it playing out in a more modern setting. Okay, so the basic idea is that you've got a potential and you're building in an m squared chi, which goes negative, then positive, and damps down. The only reason for getting it to go positive is that you ultimately want to bring trajectories that have been spread apart back together. You don't want to produce domain walls or anything. The approximation we're using for trapped inflation, using exactly the same parameters, is to put an absolute value on this. So there's a 0, and it goes up and down. And that is a very, very different system than this one. It looks sort of like what you were doing. Well, at least I think you were doing. I know Lev was doing it. Where you had m squareds. The m squared was basically going down to a 0 and then coming back up again, but it was always positive. Oh, it does. Okay, well, then we now have the full realization of this, the tachyonic brane thing. Good, good. Okay, this is in more detail. The key thing that we need to calculate is what zeta actually is. This is what zeta is. So zeta is this conserved quantity in the coarse grain, except for things that involve gradients and fluctuations. And so you can actually calculate those, obviously, in a lattice calculation, and that's what we do. And so the thing that one is approximating this in stochastic inflation is you say that this thing, d zeta, has a square root of log a, or log HA is even better variable, and then a term which is the h over 2 pi. But this is actually what it is. You can measure this. And you don't just measure an h over 2 pi, but you can do all of the gradient corrections. And so that's what we're doing. And for something that involves an instability, that's really important to get right. Right. So you've got the basic framework where this is designed so that you'll see it. So the m squared goes negative, then positive. This is what happens to the chi trajectories, not very surprising, is that you hit the instability and you shoot out. So it stretches. So you got little quantum fluctuations, which then stretch everything out. And so that's like it's building a huge strain in parameter space, which should tell you that something neat can happen, and you can interpret in terms of particle production. And then because we made m squared positive so that it wouldn't just keep going out, it oscillates back down and goes back to initial state. But the key issue here is this stretching and what the consequences of the stretching are for zeta production. The phi trajectories are also interesting. They're delayed relative to what we just saw, but they actually do develop a flanging as well because of the back action of the transverse direction on the forward. Turns out we actually saw that, much to my surprise, back in the late 80s, that there is a pullback. So you have to be a little careful. It's not just transverse only. there is some effect on the longitudinal things. This, if you take the box that we begin with for the lattice and you average zeta over that volume, this is what happens if you don't put that sort of transverse instability on. Zeta basically is almost a constant. You can't even see it. What's what? Well, in this case, it's phi and chi. It's the inflaton direction and transverse direction. The more fields there are, the more terms will contribute to this. And this is what happens to the mean zeta over that volume. It fluctuates. But the better way to look at it is in terms of individual places on the lattice, what happens to the zeta. The way we get this is basically by integrating this term, which has the Laplacians in it, but it's also got nonlinearities in it. And so you start with zeta, and then you get these remarkable, perhaps not surprising, flanging trajectories. This is relative to where you don't have that at all. And so you can see that you've produced a huge amount of zeta. But how did you do this? Well, there is a term which is associated with the classic stochastic thing, but that's not the dominant thing that's occurring from our perspective, but we have to explore this in more detail. What we think is happening is that you're doing this big parameter stretch, and you are, in effect, creating particles with, you've got this whole system, which is a field system, and you've got it under heavy strain. And so, therefore, what it's trying to do, it's trying to solve the problem by spitting off particles. And so that is what the phenomena of zeta production is, because if you turn off fluctuations, zeta is conserved at each point. And so that phenomenon, we put the fluctuations in at the beginning, but then we turned it off. We didn't keep a term driving the quantum fluctuations throughout the calculation, just like Jonathan didn't. It's probably true that that's a good idea to do it, but we didn't do it, and we didn't want to do it. And so all of this effect is due to what is, in effect, the response to having done this extreme nonlinearity associated with the instability.
So if I have a single field, just one field, would this equation hold?
No, but there is an interesting phenomenon that occurs. The fastest heating that we've ever seen, and we did a little bit of exploration, we've got a lot more to do, was roulette inflation, which just happened to have a potential that passed through an m squared equals 0 region, an m squared negative. And so what happened is you came along an inflaton direction, and it oscillated, but it didn't oscillate very much. So it was pretty amazing. So it is not true that the folklore that if you just have an inflaton, it just goes oscillating back and forth and back and forth. You can arrange the potential shape in order to have actually pretty rapid heating. But the question is, can you actually get an anomalous zeta from that? And I don't think the answer to that is no.
You don't think the answer is no?
I said I think the answer is no. Are you trying to put words into my mouth? Okay, so you got the scenario, and this is the 2-point burst, d delta zeta squared by d ln a. So it is really like, it's the square root of that, that's the stochastic kind of term that you try and put in on the stochastic inflation side. It's the analog of h over 2 pi root epsilon, d Gaussian random variable. And this is what it looks like. So it's fairly concentrated. There's a characteristic A scale where we stuck this transverse potential phenomenon. And then we have a few control parameters. We can control the size of it. Originally, we weren't very happy about the huge magnitude of this. We said, uh-oh. But then we had it was really ruled out by the data. But then we had the you could call it luck or whatever. Where we set it, it's only a few, not too many E-foldings before the end of inflation. If we put it at 45 E-foldings or 50 E-foldings, this stuff, no chance. I mean, we could control the parameters and make it really tiny, and so that would be a neat effect. Here, this is about 1,000 times zeta over this, which means I would say primordial black holes would just love that regime. Anyway, I don't know. But what's that? We want zeta to be almost unity. I don't think you need it to be that high. Anyway, this is the 3 power, the 3-point power, similar one for the 4-point. So you get these bursts, and the bursts are not just localized to being 2-point, so that it's a really non-Gaussian distribution. We haven't really looked at that in terms of making nice, pretty movies. There is that. The more stretch you have, the more important it is. Then there's overall amplitude. And what we were trying to do was to have this amplitude of the transverse thing big enough so it has an effect, but not so big that it completely dominated the inflaton transport. So essentially, this is an inflaton plus something. This is the 2-point power for our model of trapped inflation, which, as I said, we put an absolute value. And these are all the residual of the quantum, quote-unquote, quantum fluctuations we put in. We have to do this a lot more carefully to get it done because trapped inflation is subtle, as you who have worked on it know. But this is a pretty interesting way to try and compute it using the lattice code that should get it with high accuracy. And what's interesting is that it's really complementary to having the instability or not having it. And now I have the language for it, which is some anti-brains and brains. Just kidding. 3 power, same thing. Yeah. Yeah, but you know, stochastic inflation, it really is quantum because the term that's in the fine grain that's feeding into the coarse grain has h bar in it, right? So it is I mean, it's the same phenomenon. I mean, you took it into account. We took it into account in a different way. Yeah, well, that's what I'm, and so that's what this slide was about. I'm really interested in trying to do the translation between the two methods because my feeling is that with these kinds of instabilities, what's actually happening is that it has a particle description, but it's like burst particles. It's not like, you know, I'm going to do a Feynman diagram where I do this. It's actually multiple particle production, often soft, around the characteristic Kp. And so this framework allows us to resolve all of that. Okay, so I won't get this into detail, but we have a neat relationship that entropy is intimately related to occupation index, and that's a much, much better way to deal with occupation index. And so this is actually showing occupation indices for different wave numbers. I don't think it'll do much for you, but it does. It just shows that you create big bursts of occupation if you want to interpret that way as associated with the instability. And this is the occupation of zeta, occupation indices for zeta for various wave numbers. And so the way to interpret that, or at least the way I like to interpret, it's what you're doing is, yes, you're creating phi's and you're creating chi's, but you can also say I'm creating phonon bursts, and that's what a zeta is. It's a phonon burst. Since we have to get to drinks, I will pass through beautiful pictures, which I would love to have you marvel at. If you aren't saying wow now, what can I say? No, no, I know what you're saying. You're going to say, so he says, whoa, not wow. Okay, this is without, this is with, this is what Jonathan showed. Okay, this is really wow. And not just because it looks complicated, but actually I think that this is the framework. Anyway, it's the framework that we're trying to develop for a modified way of looking at stochastic inflation that fundamentally involves coherent states, so that you know, in stochastic inflation, you have a Langevin network that has the fluctuating component. It's got the classical drift, and that's what the update's all about. If you think about a system in which you have a state which has got a condensed or coherent aspect, you can actually treat the fluctuations in the condensate as one entity. And you have to evolve that system. And the idea that I think is really neat is that you can act on the initial condensed state by an operator, which is the classical displacement operator that people use with coherent states, that does the fluctuation step. That is the stochastic kick step. And then you act on it by the drift step. So you do kick, drift, and it's not unlike what you do with any path integral. You do, basically you're doing the same thing, actually. You're doing something in k space, something in position space, k space, because I mean, that's just a standard path integral. And so that framework is at least it's a self-consistent quantum framework. And there is a specific form for the fluctuations, for the drift operators, and what's interesting about it is that in that description, the condensed state, the state that's outside of the horizon, is actually got lots of occupation in it. Whereas usually we're thinking of, oh, you see, I have this evolving k equals 0 thing, and then it's all Bunch-Davies vacuum. Is that really a good description of the system? Because what you're doing is every time that you've got the coherent state changing, you have changed the nature of the fluctuations that are operating inside the horizon. And so it's like, you know, that's what stochastic inflation is all about. It's all about back action. And so there is an intimate relationship between what's large-scale coherent and what's short-distance fluctuating. And those things have to be handled in the same way. But there's no reason that it shouldn't be. And it's actually, I can even use some keywords, which I won't. But I am going to leave it at that is the thing that I have the most fun with. But I can't say that I've got, I mean, I can put it into the form of stochastic inflation that does have a quantum mechanical element. But the question is this a modification of the system? The one thing I will say is that people do, with coherent states, Wigner functions. It's just another approach, because instead of the basis being a complete orthonormal basis, it's an overcomplete basis. And you can actually clean out the basis a lot. And I think it's just the generally best framework to treat this problem that connects to, let us recall, when you have an alpha particle decay, do you really want to have your probability distribution always have arbitrary angle? Or do you want to take into account that the states can break up into the specific angle that you will observe after the fact? And that's like a coherence, and that's what this description could do. And the thing that would then become the fairly classical thing is the outside of the horizon classical evolution. but it would still have all of the quantum mechanics attached to it. It's just that it's in the framework of these coherent states. And that's what I'll end on. Wow. Oh, no. Whoa.